Good afternoon, everyone. Hello and welcome to MIT's 2016 Open House Distinguished Lecture Series. My name is Sina Buashagi, and I'm a junior in Course 2 and 18, and for the non-MIT in the crowd, that's Mechanical Engineering and Math, respectively. It is my pleasure to introduce our next speaker, Professor Maria Zuber. Dr. Zuber is the E.A. Griswold Professor of Geophysics and Vice President for Research at MIT, where she has the responsibility for research administration and policy at the Institute. She foresees MIT's Lincoln Laboratory and over 60 laboratories and research centers on campus. Dr. Zuber's research bridges planetary geophysics and the technology of space-based laser and radio systems. Dr. Zuber is the first woman to lead a science department at MIT and the first to lead a NASA planetary mission. In 2002, Discover magazine nagged her one of the 50 most important women in science, and in 2008, she was named to the U.S. News Harvard Kennedy School list of America's best leaders. In 2013, President Obama appointed her to the National Science Board. Please join me in welcoming Professor Maria Zuber.
Okay, thank you, Sina. Hey, thanks everybody for coming. It's Mars, yeah. So, yeah. All right. How many of you people are scientists or engineers? Okay. All right. Cool. We got something for you. All right. How many people who have ever looked up at Mars in the sky at night? Okay. Okay. All right. How many of you have seen The Martian? All right. Okay, we'll talk about that. So, all right. So what I'm going to do today is I'm going to talk a little bit about what it would take to do a human mission to Mars. So, there are really no serious impediments other than psychological impediments. The science, we know lots of science, the technology, technological problems can always be solved, okay? It's a money and political will issue and a question of it would be expensive, and you'll see why, okay? But so let's just start and think about why we would want to do this. Okay, I love Ray Bradbury, The Martian Chronicles. I grew up reading. So we're all children of this universe, not just Earth or Mars or this system, but the whole grand fireworks. And if we're interested in Mars at all, it's only because we wonder about our past and worry terribly about our possible future. Okay, so what does that mean? Okay, so why do we explore in the first place? Okay, well, the grand challenge of doing something difficult, national pride. If and when we send a human mission to Mars, it won't be a United States mission to Mars. It will be an international mission to Mars. It will take all the smart people that we can find to help us do this and participate in it. Competitiveness. If the things that we teach our students to do, the students who work for me, they don't all grow up and go into the aerospace industry. They go someplace, but the skills they have. Any employer would want to have somebody who has those skills, okay? And so getting a young person really jazzed up about doing something really difficult that's fun, okay, is really a great motivator. So contributing to the technology workforce and infrastructure, having the ability, having factories that can do really precise machining and building really complicated electronics does a whole lot more than just help the space industry, okay? Let's see, learning to live and work in a low G environment. the last people that we sent off of Earth that were in a non-Earth gravity field but not weightless was when we sent humans to the moon, which was 1/6G. And so we don't have the right spacesuits. We don't have the right kind of any kind of the right hardware. Well, we'd like to discover things. I'm a scientist, so discovery, that's my thing. And this, the worry about our future part, the preservation of our species. So there are some, and I'm an optimistic person. I'm not a fatalistic person, but some, like Elon Musk, feel like we must go to Mars because in case we're stupid and we, blow our whole planet up, that we have to have the species in another place. So that's not my personal point of view, but some would say that. Okay. All right, so Earth and Mars. So here are pictures of Earth and Mars to scale, okay? So Mars is about half the size of the Earth, okay? And here's a good piece of cocktail party trivia, okay? Mars is about the same size as the Earth's core, okay? That's coincidental, okay? Distance from the sun, okay, well, we call the distance from the Earth to the sun, the average distance from the Earth to the sun, an astronomical unit. So Earth is by definition 1, and Mars is on average 1.5 times as far from the sun as the Earth is. So it has a correspondingly smaller flux of sunlight. The surface gravity is about 40% of Earth. It's 3.7 meters per second squared. Here's another coincidence. So the Earth's day is 24 hours, and Mars's is 24 hours and 37 minutes, okay? Now, 24 hours and 37 minutes sounds a lot like 24 hours, okay? Unless you've got a lander on the surface of Mars, in which case you have to live on Mars time, okay? And then a few weeks of living on Mars time it's like worse than the worst jet lag you would ever have, okay? So Earth has a nitrogen-oxygen atmosphere, Mars has a carbon dioxide atmosphere, and Mars has a lower surface pressure. So we're going to talk more in detail about the atmosphere of Mars. Okay, so the Martian atmosphere is 95% carbon dioxide, and the average surface pressure is 520 pascals, or 1/200ths of the Earth, and so the pressure at the surface of Mars is equivalent to the pressure of the Earth's atmosphere at the altitudes that spy planes fly, okay, at 100,000 feet, okay. And so the Martian atmosphere, it is very thin and it is very tenuous, okay, and it doesn't hold heat very well, okay. So here's a good fun fact. The surface pressure varies by up to 1/3 over the course of a year, so 33%, okay. On Earth, the biggest atmospheric pressure change that we get, if you were in the center of a strong tornado, it would be about a 10% pressure difference, okay? So on Mars, the atmospheric pressure varies by 1/3 over the course of the year, and it's from CO2 in the atmosphere exchanging between one polar cap and the other. The polar caps on Mars, at least at the top, are made of CO2. Underneath the CO2, the frozen CO2, there's water, okay? Water vapor. So there's a lot of water underneath Mars, and we're going to talk about water because that's a totally important thing regarding sending humans to Mars. But water vapor is a trace constituent of the Martian atmosphere. And so if you took a column of the Martian atmosphere and you took all the water in that column and you squished it down, it would be 10 microns thick, okay, where a micron is a millionth of a meter, and a meter is 39 and some inches. Okay, so tiny, tiny, tiny amount of water in the atmosphere. The average temperature is minus 63 degrees Fahrenheit. Actually, in the summer, at low latitudes, the temperature can get up to about 70 degrees, okay, which sounds downright balmy, okay? But the atmosphere doesn't hold heat very well because it's so thin. So, so if you could live on Mars without a spacesuit, which you can't, and it was the summer and you were in the low latitudes, your feet would be 70 degrees, but your head would freeze. Okay, okay. And so if you could have a pitcher of water on Mars in the liquid form, which you can't, but if you could, and you poured it out of a thermos, it would freeze before it hit the ground. Okay, so so it is, it's a great place, but it's not the most hospitable place. Okay, all right. Lots and lots of dust. So dust is a huge, huge, huge consideration for Mars because dust gets into everything. And when you got a machine, think about anything that it's got to turn, wheels, doors. You gotta have dust. You got to take into account dust. Okay, and obviously, liquid water is not stable at the surface. Okay, but I'm saying pure liquid water. We're going to come back to the liquid water on the surface part. So because it does appear that very salty brines are metastable on the surface. Okay, so here's just a picture of the same place on Mars at two different times, and taken from one of the cameras on the Mars exploration rovers, and you can just see the difference of how the atmosphere changes. So the atmosphere is very, very variable. Okay. Okay. So Mars is also far away. Okay. So this is a picture of the Earth-Moon system. Okay. And this picture was taken from a camera in Mars orbit. Okay, so so I actually have this picture in the wall of my office, and every time a student comes in and they say, "Oh, I want to go to Mars someday," I point to this picture and I say, "Everything you know and love, is really, really, really far away." And you would have to leave all that. Do you want to do that? And they all say, of course, yes, sign me up. Okay, all right. So so this picture was taken from the Mars Global Surveyor spacecraft. So, okay, all right. So here is a picture of Earth from the surface of Mars. Okay, so you see. So there it is. Okay. So, and think about it, isn't it cool that we can figure out where Earth is in the sky and then tell a camera on a rover to point to the right place and set the exposure so we get the right amount of light in it to get that? So that was, yeah. So. Okay, so now let's talk about going to Mars. So this is a nice picture of the launch of the Pathfinder rover, okay, from the 1990s. Okay, so going to Mars is not that easy. Okay, in fact. Most Mars missions to date have failed. Okay, so here everything in red failed and everything white succeeded, and this was my call, and I set the bar really low for what determines success. So, and in fact, in our there's some lore, in fact, that there's a great galactic ghoul that eats spacecraft when they get close to Mars. Okay, but this is it's just a theory. We have never seen this, and so that's just an artist's conception. So, about 40% of Mars missions have failed to date. The orbiters have been more successful to the landers, and that's the bad news. Okay, but the good news is, okay, that that we're doing better than both Ty Cobb's lifetime batting average, and he was considered successful. Okay, all right, or Ted Williams. Okay, when he had his magnificent season in 1941. So, and of late, we've had more successes than failures, but you know, things can just go terribly wrong. It really is difficult, and we've got a couple more en route. So, so this is an evolving story. Okay. All right. So if you want to go to Mars, you need a rocket, and all right, here's a rocket. This is the Space Launch System Block 2, which is proposed to be able to take humans to Mars. It's a heavy lift launch vehicle. This would be the third generation of this launch vehicle, but not even the first generation of this launch vehicle exists yet. Okay, and this so the SLS Block 1 is under development. It's a $7 billion development effort. Okay, and the Block 2 would be considerably more complicated, and I have no idea whether this will come in on budget. Things in the human space program tend to be less close to coming in on budget than on the robotic side of things. Okay, we need a crew vehicle. Okay, so this is the Orion. So on here, this is the only piece of hardware that actually exists. Okay, that's in the least bit relevant. Although this is not what we would send, but this is a new crew vehicle that would be rated for taking astronauts out of Earth orbit, and it's not that big. You know, I mean, if you compare this to the Hermes and the Martian, you know, this is well, it would be cozy. Let's put it that way. We'd need something bigger than this. We would need a surface ascent and descent module. So I just took the one from the Martian since we don't have one, as well as a space transportation system. So, so take a look at that because I'll show you one of the plans for one of them that NASA has under development. Okay, so, all right, so there are, so you can launch to Mars once every 26 months. Okay, that's the launch window, and so you've got several weeks where you can launch, and so if you're going to send people there and then bring them back, there are kind of two classes of trajectories that you can explore. So either short stay or a long stay. So in a short stay, okay, so this is the orbit of Venus, Earth, and Mars. Okay, so in the short stay, you launch from Earth, so you head over to Mars, you arrive at Mars, and then, so it takes about 6 months to do this transit here, and then, so you can stay 1 to 2 months on the surface, and then to come back, well, Earth's not in the right place, so Earth is not here when you're here. And so what has to happen is you come in and you go to Venus, okay, and get a gravity assist from Venus, and then you come around and come back to Earth, okay. So this minimizes, if you do this, it minimizes the time that you're away from Earth, okay. But you're spending a lot of time away from Earth and not too much time at Mars, okay. So, or you could do a long stay and say, well, if we're gonna go, we wanna spend most of the time on Mars. And so, so you can launch from Earth, you get to Mars, and then you stay, so it takes about the same time. You stay on Mars then for about a year and a half, about 550 days, and then you can take a straight shot back to Earth, and now Earth is in the right place, because Earth has gone around the sun again. And so the full mission duration here is about 2.5 years, okay? So it's a long time, okay, to go. And it doesn't, it actually doesn't matter too much what your thrust is. You know, I mean, a little more thrust, a little less thrust. You know, we are victims of celestial mechanics, okay? You know, Earth and Mars have to be in the right place for this to happen. Okay, all right, so radiation, okay, so one of the things that the Martian, the book and the movie kind of just glossed right over is radiation, okay? They just said, oh, we shielded for it, you know, we corrected for it. But radiation is actually a huge deal. So we have made some measurements of radiation from Mars orbit. And there's an instrument called MARIE, which measured galactic cosmic rays and solar energetic particles, okay? And so here's a dose over a particular orbit. So all this stuff down here, this is the galactic cosmic rays, and then you get these solar energetic proton events. So you get these big spikes. And then just based on the cosmic rays, which are kind of quasi-uniform and not taking into account these kind of stochastic peaks here, you can just take the cosmic rays and then say, all right, on average, on a year, what's your dose on the surface of Mars? And so this is high doses are here in red, and low doses are here in blue. And so this is accumulated radiation, okay, over a year. And this actually looks a lot like the Mars topography map, okay, where red is high and blue is low. And the reason that the doses are much lower here is that these are the lowest elevation areas, so there's more atmosphere shielding the cosmic rays and the solar and energetic proton events from that. Okay, but we have better information now because the Curiosity rover, which is at Mars right now, has collected radiation measurements from Gale crater. Okay, so again, we have these the cosmic rays, the galactic cosmic rays, and the energetic particles, and so radiation. You'd say, okay, well, Mars is farther away. It's 1.5 times as far from the sun as the Earth is, okay? So, and the galactic cosmic rays are the same everywhere. And so why aren't the solar and energetic proton events worse, all right? And there's really two reasons, okay? Mars doesn't have a magnetic field, and the magnetic field shields these particles from coming to Earth. And Mars also has a thin atmosphere. So thanks to these collective measurements, we do, however, know that radiation is not a showstopper, okay, for doing a human mission to Mars. So the best estimates that we have for a long duration mission would bring humans back to Earth and have an accumulated dose that's kind of the maximum allowable dose that you could really have, and it would correspond to increasing your cancer risk by about 5%. Okay, and so if you worked in any industry that dealt with radiation, that would be the maximum lifetime accumulated dose that would be allowed for you to have exposure. Okay, so but that's good news because and you can always shield against radiation, but shielding is really, really, really heavy. Okay, so and so that's a problem. Okay, All right, okay, power, okay. So if you're on the surface of Mars, you don't have as much sunlight as you have on the Earth, and so you need to have power. And there have been all kinds of studies done to estimate how much power one would need at day or night. Usage, okay, at night you have to stay warm. In the day, the sun is useful in having us require less power. So there's a couple of ways you can do that. This is a model of a possible mobile. So if you go to Mars, first of all, it's going to be nuclear. Okay, you've got to use a nuclear reactor. Okay, there's no way to get enough power just using solar. Can't be done. Okay, game over. All right. So here's actually a design by NASA that actually looks a lot like what Mark Watney used in The Martian. This is the nuclear generator here in the back seat, and here are the solar panels that put out that charge during the day. So, this is an actual design by NASA. But what's more likely to happen is that you would take a small generator, you would bury it, and then you would surround it by water, okay, to absorb the neutrons and reduce the radiation. And the weight of water that would be required to shield this is as much as the weight of the reactor itself. So the weight of this reactor that one would have to take to have enough power to use is 3,300 kilograms. Okay, so it's heavy, okay, and that's a problem. Okay, so there have been calculations that have been done that have showed the amount of mass that one could take for different kind of scenarios. So here's a short stay, here's some longer stay scenarios, and so here's the landed mass and various other parts of the system. And so you're up here at 100,000 kilograms or so, and that's just to put that in some kind of a context. It costs, I would say, about $20,000 per kilogram to get something off of the surface of the Earth. Okay, so it's so you don't want to take anything with you that you might have there. Okay, so because it's so expensive to send it. So so one of the things that is explored is something called in situ resource utilization, and one of the things that you would do there is make your own rocket fuel when you're on Mars. Okay, and so there's actually a test that's going to go. The Mars 2020 rover has an MIT experiment on it, an experiment that's called MOXIE, and what MOXIE is going to do is take carbon dioxide from the air, and which is CO2, and separate it into CO plus O, okay, and make liquid oxygen as a rocket fuel and demonstrate that, so that you wouldn't have to take rocket fuel with you to get off the surface of Mars. That'll be the first demonstration of in situ resources. Okay, rocks. Okay, well, you must land safely. Okay, and so I would say in planetary science now, landing on Mars is the hardest thing that we do. Okay, and the reason that it's hard is that the atmospheric pressure varies a lot. The atmosphere is turbulent. Okay, the Earth's atmosphere, if you've flown in a plane, you know that the atmosphere is turbulent. The atmosphere of Mars, even though it's thin, is also turbulent. And you have rocks all over the place on the surface. And And so actually in experiments where we've sent landers and put airbags, there's actually a wind limit of 20 meters per second that you shouldn't land on Mars with airbags if the wind is more than 20 meters a second, because if they come down and hit the rocks vertically and the wind is blowing, it's going to shift it this way, and any kind of material is not as strong in shear as it is just in a normal force. And actually for the Mars exploration rovers, the first one landed, and then the second one landed several weeks later, okay? And in the meantime, a dust storm kicked up, okay? And the dust storm heats the atmosphere and causes the winds to blow. And so I was one of the reviewers looking at the landing, and we spent about 2 days trying to decide whether or not to open the parachutes 2 seconds earlier to compensate for the warmer atmosphere. And of course, if you open them earlier, to slow it down more as it's coming in. But if you open it up earlier, it's going faster, and so it's a greater stress on the cables of the parachute, and so there was worry that the parachute would break. But I think the surface wind velocity was like 18 meters per second when it finally landed. So it's very challenging. Okay, dust storms. Okay, they are pervasive on Mars. Here's a dust storm that's blowing off the North Polar Cap. Here are LiDAR returns from the atmosphere showing the distribution of dust. The way that dust gets lofted into the Martian atmosphere, this dust is a micron in size, so it's very, very fine, and so it doesn't take much wind at all to loft it. So here's a dust storm on the surface. Here's a LiDAR map of a dust storm. And these are dust storm tracks at one of the Mars exploration rover landing sites. So it's not like, oh, every once in a while you have a dust tornado or a dust devil coming. Okay, so now I'm going to show you if this works, which I hope it does. This is a movie of dust devils at the Curiosity landing site. So yeah, so there they come. So this is what it's like all the time, okay? All right, so you need to worry about that. Okay, so the global dust storms on Mars happen every Mars year, and one Mars year is about 2 Earth years. And so the global dust storms, they usually start in the southern hemisphere and during the southern hemisphere summer. And the reason for that is because Mars's orbit is more elliptical than Earth's orbit is, and Mars is closest to the sun in southern hemisphere summer. So you have the greatest warming there. So here, blue is clear and red is dusty. And this is a bunch of thermal images that was taken starting in June, in mid-June. And you can see here by the beginning of July, there's a dust storm that is growing and growing. And you know, when they take off, they go global in about a week, okay? And what happens is, so these dust storms start, you kick up dust into the atmosphere, and then and the dust heats the atmosphere, and it makes it warmer. And then, so this area is warmer, this area is colder, so you have a pressure gradient, and it makes it windy. And the extra wind kicks up more dust from the surface, which makes it dustier and changes the pressure gradient even more. And so it's a positive feedback effect. And so, so this is the difference between a clear atmosphere then and a dusty atmosphere for that particular dust storm. And so it's true, dust storms are a big deal on Mars, and at the beginning of The Martian, you saw that you know, they left because there was this big dust storm that came. First of all, it wouldn't come in quite that fast, and it couldn't, because the Martian atmosphere is so thin, even if it was really windy, it couldn't blow over a spacecraft. Okay, so that was, Andy Weir took some liberties with that. Okay. But it's this tau is it's a property called optical depth, and this just shows you. So this is taken from the Opportunity rover. So these are just pictures of the surface, just showing you an optical depth of 1 basically means you can't see. Okay, and so Mars commonly has very high optical depths where you just can't see anything. And then the atmosphere is thin, but the dust is so thin, it's a micron, that it takes months for the dust to settle out of the atmosphere. Okay, so and anybody going to Mars is going to have to deal with this. Okay, because you're going to land, you're going to want to be there in the summer when this happens at low latitudes. Okay, and then. So here's some Apollo images. Just look at how the dust gets into everything. Here's one of the Mars rovers. You can see the dust all over the solar panels, so that the solar panels lose efficiency. Here, astronaut, filthy. Poor Jack Schmitt. Look at how dirty they are. Okay, so it's dirty business. Okay. Locomotion. Okay, I'm not going to go into detail describing this slide. This is the square root of a Froude number out there for anybody who is a scientist or an engineer. Okay, and so all that I want to say about this is that human locomotion is optimized for 1G. Okay, so if you are at anything other than 1G, you are non-optimal, and you are expending more energy. There's just no easy way to get around, okay, looking at this from energetics. So, for the moon had such low gravity that the spacesuits actually supported themselves, okay? But that's not the case for Mars. The spacesuit it would be difficult for a human being to have mobility with that space suit, and on Mars, though, actually, it looks like this is actually some research that was done by under the supervision of Dave Newman from MIT, who's now the NASA deputy administrator. Who showed that it might actually be more efficient on Mars to run than to walk. Okay, but you would need to design a suit that had enough mobility to do it. So we need a new spacesuit, and this is just more Apollo data showing you that this stuff gets studied in great detail. That just showed that you expend a lot more energy. On a walking traverse than if you have a rover, so you really want to take a vehicle with you because it's going to be very difficult for the astronauts to get around. And let me tell you, in geology, you don't want to go on the flat, smooth places, okay? You want to go on the rugged hills like this. And so a lot of effort is underway looking at how human mobility, how they would climb and get around and go to all the very interesting areas, and these are not all areas that you can take rovers to. So a great deal of effort goes into the mobility of how humans would actually work on the surface of Mars, and what the interplay of humans and robots would be on the surface of Mars. So Julie Shaw from our Aeroastro department works on that. Okay. Water, all right, so if you send humans to Mars, you need water, okay? And we know it pretty much exactly how much water Mars has on the surface, and this is another good cocktail party trivia. This is 85% of the Greenland ice cap, okay, is the amount of water that is on the surface of Mars. Okay, but it's frozen, okay, and And I said that liquid water wasn't stable on Mars, but it looks like salt-rich water actually does flow on the surface of Mars. And these are some images that were taken from the Mars Reconnaissance Orbiter spacecraft. And what I want to call your attention to is these flows. Sometimes they're there and sometimes they're not. You only see them on equator-facing slopes when the temperature goes above freezing. Okay, so small amounts of water are liberated from very shallow depths beneath the surface and flow out there, and so they're accessible, and but they would need to be purified. But it's a lot easier to take a water purifier and get water than it is to take water with you. So I'm going to show you the same image here. So this is now reprojected. So if you were flying along that cliff in a helicopter, this is what it would look like, and you can see here these flows of water. So this is metastable liquid water on Mars. Okay, so that's but at shallow depths beneath the surface, there is frozen water, and there is a lot of it. Okay, so this is a view of the North Polar region of Mars, taken by a neutron spectrometer, and the blue means no neutrons, and no neutrons means water. And the way this works is galactic cosmic rays come in, and they knock neutrons off of water. Water captures the neutrons and makes heavy water, and then neutrons don't come off the surface. So whenever you're missing neutrons, you know you have water. And this instrument can sample down to about a meter depth. So there are places in the high latitudes of Mars where there is vast, abundant, frozen water within a meter of the surface. Okay, so you really don't need to take water, and we know where it's at. We know where it's at. Okay, but we wouldn't necessarily want to land at the poles because of energy considerations and lighting considerations. And so at low latitudes, they've been mapped in detail. And so here's a particularly good area in the vicinity of the Schiaparelli crater. And so in this area here, it contains the highest water content in the region, so more than 10 weight% water, so which means that that's so much water that the water can't be held up in a mineral matrix. So it could be that would be a good place to land. So there is actually, from a accessible water standpoint, exactly where you would land if that was a consideration. Okay, so then. All right, so that's it. In geology, you always end a presentation with a sunset. Okay, okay, always. Okay, and on Earth we have blue skies and red sunsets. Okay, and on Mars we have pink skies because of all the dust in the atmosphere, but we have blue sunsets because when the sun passes through, blue wavelengths get transmitted most efficiently. Okay, and so this was a picture taken from the Curiosity rover in Gale crater. And there is there is a NASA continually studies and updates scenarios for putting humans on Mars. And it's the latest one, I think, came out in about 2011 or so, and it's about like 500 pages, and it's all engineering wire diagrams and things like that. But if you are interested in that kind of thing, and let me tell you, it's great reading, okay, if you're so disposed. You can just download it online. Okay, thank you very much, and I'll be happy to take some questions. Okay, right there.
What do you think about some of the non-governmental projects like the Mars One?
The non-Mars. So I'll tell you that, the government's in a difficult situation because the public is risk averse. Okay, and so you have to have a very, very high probability of success. If the government does something, and so the non-government efforts. They're a long way from being where they need to be, but this is going to be like the exploring the new world. Ships go over the horizon and you don't see them again, and eventually one gets there.
Do you bet your money on a government agency or a non-government agency landing first?
At this point, I would say government, but I'm pulling for the non-government. I would help them. But it's expensive. So, any other questions?
Thank you.
Maybe wait. Let's wait a minute for people to leave who are going to leave, and then we'll answer the questions. Okay. Wait. We're gonna let some people leave, and then we'll answer some questions. Okay. Okay, next question. So, right there. China's plans. Yeah, China has very ambitious space plans, and their near-term plans are for the moon. Okay, and they're currently working on another moon rover to put there. But they both have plans to put humans on the moon and a rover on Mars, and their technical capability is increasing. So, yeah, right there. Okay.
In the Martian, they asked China for help.
Well, China actually offered help, and they accepted it. So yeah, that's why everybody, we should all work together on this, right? So, okay, one over there, yeah.
I have a quick question. So, from an optimistic point of view, when would you expect people to get actually the food on Mars?
So I mean, the planning is for 2030. Okay, but NASA also planned to return samples from Mars by 2005. Okay, and we haven't done that yet. Yes, okay, yeah.
So there are so many movies like sending people to Mars. So which is your favorite one?
Oh, The Martian is the one that's closest to yeah.
How about the mission to Mars? Have you watched that?
Yeah, it's they're all good, I mean, this is you kind of like if you gotta kind of put a lot of what you know on the shelf for a couple of hours, right? And just enjoy it, right? But the Martian is pretty close. So Matt Damon's speaking at our graduation, So yeah, so yeah. Was there a question back there? That's anywhere? No. Yeah.
Which technology do you think would help us the most in feeding all of our astronauts out there?
That part was accurate, actually. That part was accurate. So people, there's a lot of research on growing things on Mars analog soils, and so that's been studied. That was pretty close. But the most important thing about going to another planet is getting off the Earth, Okay, so most of the energy that gets expended is taking you out of the Earth's gravitational well. Okay, so the most important technology is a good heavy lift launch vehicle. So why don't we start from the, so there are discussions that we should go back to the moon first, because we have to learn. We have to learn how to be off planet again. We have to learn how to work in non-weightlessness again. You wouldn't use. There are different energy requirements. You would need a different spacesuit because of the different thermal conditions. So there are and it's not Mars, right? So I think there are arguments pro and con. I personally think that what will happen is sending a crew vehicle just to do an Apollo 8-like thing, where flying around Mars and then coming right back, and we would learn a lot by doing that. Right there.
So I know you've been advocating for more funding for science and technology, as have been lots of different areas. What do you find are the main impediments to that?
The main impediments to funding for science and technology. So overwhelmingly, the Congress is supportive of investments in science and technology because they realize that our national competitiveness derives from our innovation. And the impediment is really just medical costs and Social Security costs. And it's just that those numbers are increasing and increasing and increasing, and space science funding, along with kind of everything else, is in the discretionary bucket, along with veterans benefits and other things that we, energy and lots of cancer research. All these things are like super important, and that bucket keeps getting squeezed and squeezed and squeezed because the medical costs and Social Security costs keep increasing and increasing. So, yeah.
Curiosity was blocked on Mars on a stone. Is it still blocked, and is there any plan to unblock it?
You bet there's plans to unblock it. It was still blocked last time that I looked, but it's you really keep they'll get it. Keep at it, yeah.
Technology is exponentially becoming more and more powerful. We're in a technology era, and all companies now are sort of spinning themselves as technology companies, because you can't be a company and not be a technology company nowadays. What do you think, what is the key innovation area, or the key opportunity? Where would the leap come from that would get us from point A to point B? Because we're going to get there. It's just a matter of where is the innovation going to come from, and where do you think it needs to be focused on?
So for a Mars mission, or you just in general, there's this is, so I'm responsible for all research at MIT. So it's a if I say one, I'm going to get a lot of other people around here mad. So.
We know there's a lot of technological innovation across the business right now. What I'm saying is, where could you apply that to space travel? And what exponential growth needs to happen in technology to get us there?
So I would say in heavy lift, so we need it in the kind of propulsion area. Although I think that we could do that. I actually think it's going to be in software. Because when things go wrong in space, let me tell you, because I have personal experience in this, it is never the super high tech, FPGA. It's always somebody not zeroing out a do loop. Okay, so that's the lander that crashed at the South Pole of Mars was not zeroing out a do loop. So it's innovations in software, I think, that are really going to be the game changers. So, but I was another thing though. If you want to take hardware, materials, advanced materials, lightweight materials, radiation-resistant materials. There's a whole lot to be done in that arena as well. Yeah.
You just mentioned propulsion as one of the areas in which you expect improvement. There's different fuels that are being researched, is there anyone in particular that you feel optimistic about, any one group's research?
Yeah, that, yeah, I wouldn't pick a winner in that one. NASA's looking at like 3 different variants on that, and we'll have to decide. So, yeah.
You said that solar energy wouldn't be possible on Mars. Could you explain more about that?
Oh, no, I didn't say it wouldn't be possible. I said it wouldn't be enough. Okay, so because the sun doesn't provide you with as much energy as you need to do all the functions that you have on Mars, and we even if you let the sunlight build up, we don't have good enough batteries. So batteries would be another enabler. So that's it. Yeah.
Radiation exposure during travel time to Mars and back is not a concern?
Yeah, it is a concern. Yeah. So in a 6-month trip to Mars, it's about 20 to 40 rems. Okay, if that means anything to you, which is a substantial exposure for a worker in a nuclear plant. It would be that's substantial, but it's not a game stopper. Okay, but you could you can always reduce that by shielding, but shielding is very heavy. So it's these are the reason that I'm saying these are engineering trade studies, right? So you can trade off it's dollars, mass, radiation. There are just trades here, and you just do the trades, and you set your risk accordingly. So, yeah.
What do you think of that latest project of sending these very small items over to like Pluto at very high speeds with this solar kind of thing? Solar winds.
It's bold. How about that? So. It's you got to go within a half a solar radius to the sun, so it'd be cooking. I've hardest instrument that we ever designed, I ever worked on the design of, was one to go in orbit around Mercury, because it just fries. Think about the leads on your electronics, the thermal stresses, because it's going to go there, it's just going to get hot, 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 and then it's going to flip around, and then it's going to get cold, 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 and you got to be able to design for that whole thing. So how you do that with a small mass, that's you solve a lot of problems with mass, and they don't have mass. So it's a good problem to work on. So, yeah. Yeah.
Are there plans to deal with the influence of microgravity? Because your astronauts are going to go there for like 2 years, and then you're going to come back and then like really hard re-entry. Will they be able to survive that?
Well, one of the things that is an issue when you send astronauts into space is bone loss, and so they really have to exercise vigorously. And the good news is we have a lot of data on that from the space station, and in fact, very, very vigorous exercise. We've had a guy come back with virtually no bone loss. So you can get around that. Now, if you stay 550 days on the surface of Mars, then you're used to 40% G. So that would be interesting. Coming back, and we have no data on that. So yeah.
Do you think human beings would ever destroy the Earth so much so that it's so uninhabitable that Mars looks inhabitable? And if so, what would we have done?
Could humans? Do I think they would? I hope they don't.
If that happens, what do you think would be the number one thing that we did wrong?
Oh, it would be nuclear war. I think. Yeah. Nuclear. We have enough nuclear warheads to take out the Earth. That's what.
How about AI? Artificial intelligence.
Maybe. Climate change. Climate change. So let me tell you, climate change. Climate change. It will be horrible, but not. It would not wipe out the Earth. What it would do is well, sea levels will rise. So all the people who are along the coasts, if you think the mass migrations out of the Middle East now are a lot, that is nothing compared to what will happen when, the West Antarctic ice sheet comes off. And then, if it, we could lose growing seasons, which means that large parts of the world would, once you lose a growing season, you're at great risk. But there would be, there would be people who would be able to deal with that, but not everybody. But nuclear war could take out everybody. Yeah, this is depressing. We're talking nice. Yeah. So NASA's collaboration is pretty strong with Russia, Canada, the European countries, even some Middle Eastern countries, but not with China. So, in fact, we're not permitted to collaborate using NASA funding with China. So, yeah.
All these failed missions, and we just have more majority of them come from the United States. How much did that cost us? So the question was, a lot of those failed missions are from the United States, and what did that cost us? Well, most of the failed missions are from the United States because the United States has sent most of the missions. Okay, so our hit rate is actually pretty good compared to some others. Okay, but how much does it cost? Actually, I don't know because I haven't added it up. That's an interesting thing to do. But what I will say is that when a mission to Mars fails, okay, it's not a complete failure because sending a mission to Mars is not just buying a bunch of stuff and bolting it together and sending it. It's a lot of people figuring out how to do that. So much of your investment helps you succeed the next time. And so because this is so hard and because it's at the cutting edge, if we succeeded at everything that we did, you want to leave that stuff to somebody else. So, but it wouldn't be very interesting to us at MIT, I think. So, yeah. Want to go next?
Is the atmosphere of Mars thin enough to make meteor impacts a significant?
So the question is the atmosphere of Mars thin enough that you see meteor impacts? And yes, in fact, I took out of the talk, man, we got this picture, there's a iron meteor like this big that was found. And then there's all this work that's been done using image analysis from orbit of seeing new impact craters that were formed since the spacecraft got there because Mars is closer to the asteroid belt, so there's more junk there than there is in the Earth neighborhood. So there's a lot of new impact craters on Mars. They're not too big. So yeah.
Seems like there's lots of different open source projects within math, finding the next largest prime, with genomics, puzzles, solving by lots of people. I haven't heard as much, maybe I'm just ignorant of that area, within the space and NASA programs. Are there such open source?
Oh, no, we don't do things. No. No. Well, it's, in NASA, everything is configuration control. You don't change anything without a committee. Yeah, that's. Oh, the data that comes back. Yeah, the data that comes back. There's a lot of codes out there to analyze it, but anything that's actually in space is very, very, very tightly controlled. Yeah. So, yeah.
How thin is Mars's atmosphere compared to Earth?
How big is it? Okay, I don't know. How thin? Okay, it's at the surface, 1/200th of Earth. So it's practically a vacuum. We call it an atmosphere, but it's practically a vacuum. Okay, so we'll take two more. Okay, yeah.
So do we already send some instruments on Mars?
Oh yeah. So where do you think all those stuff came from? That's like, yeah, that's data. That's all data, except for the little clips from The Martian. Yeah. So it's data. Yeah. Okay. Last question. Okay.
Think about terraforming Mars and heating up the atmosphere.
Yeah. What do I think about terraforming Mars?
You know, I'll tell you what. Any planet is a complex system, and you know, you have to be really careful about unintended consequences. And so, so while you know, theoretically it's possible, you would have to think about what, you know, what you're ruining, you know, to do that. So I'm not. I wouldn't sign up for that one. Okay, thank you. I'm gonna cut it off now. And I'll hear the questions. Yeah. Okay. Okay. Okay.